All right, we'll start with a little bit about our machine, Focus Fusion 1 or FF1. It's actually a 12 capacitor machine. Right now, for various reasons, we're running it with 8 capacitors. So what we've got is much smaller amount of energy than people have been talking about. We put between 40 and 60 kilojoules in, and we get out about 1.2 megaamps of peak current. Compared with other similar devices around the world, there's one in Las Vegas, there's one in Warsaw. The main difference is that our electrodes are much smaller, the electrodes you saw. So I was talking earlier about the 3 legs of the Fusion tripod, but there actually is a 4th leg, because in addition you have to have a fairly efficient transfer of energy into the little plasmoid, or else you won't get significant energy out. So we've been working on all 4 of those legs. Now, I talked earlier about the record high temperatures. I'm sure people are curious, how did we measure such record high temperatures? Basically, this is time of flight. We measure the energy by time of flight, by measuring their velocity of the neutrons. The neutrons come off with their nuclear energy, and they come off with the energy from the ions that created them. And we have a near and far time of flight. And for example, for this shot, we've just plotted the energy range derived from the near time of flight and the energy range derived from the far time of flight. Once you know that energy range, then you can actually do very simple mathematics, which has been done by others, and you get the average ion energy. And that comes out to about 160 keV for about a half dozen of our best shots. Now, does this come from trapped ions or from a beam? Well, we got a lot of flack from reviewers and various other people, so we dotted our I's and crossed our T's, and basically we measured the neutrons all around with bubble detectors, which were conveniently calibrated by our colleagues at PPPL. And what we basically found was, basically you could easily calculate that using the most generous assumptions possible, only 30% of the neutrons could possibly come, and this is very generous calculations, from a beam, which creates, which would have the neutrons move in an anisotropic way, in a directed way, and about 70% from confined ions. If it's a quick question, otherwise yes. Hold it.
Did you use the energy threshold bubble detectors, or did you use the ones that go down to low energies?
Yes, they go to low energies, but they were carefully calibrated.
Well, there's an issue of room return, right?
Yeah. What?
Neutrons bouncing around, room return.
No, we did shield for that. Now, where does this come from? Well, this is a better picture than you saw this morning, a later picture of a plasmoid. Now, we take these pictures with every shot, and if we're at the right time for the particular shot, we get very similar pictures. So this is a plasmoid attached to a current, to the current sheath. And the plasmoid actually extends out here, but it's very faint. And the action occurs here. Now, this whole scale is 1 centimeter wide. So this plasmoid has a radius of about 200 microns. So we know what the volume of this plasmoid is, and we know that it is the one producing the neutrons because it's consistently at the exact same time as the neutrons. So from the time of flight, we can get the average ion energy from the images, and from the time of flight, we can get the duration of these plasmoids to be about 10 nanoseconds, which means that the ions are taking about 30 ion orbits, about 200 times it takes for waves to cross the plasmoid. So it's definitely confined. From the neutron yield we're getting and from the volume, we can derive the density, which is getting close to 10 to the 20th per cc. So that's basically where we are. Now, do we understand why we get it so hot? Well, initially we didn't. We actually had predictions of this temperature before we started working with FF1, and it was about a factor of 4 lower. So we had the pleasant task of explaining why it was higher. And the main answer is it's higher because of viscous heating. For non-plasma physicists, this is basically a process of changing the kinetic energy that you get from the compression of the plasmoid into random or thermal collisional energy. And Haynes did work on this on the Z machine, and Abel Hassani did work on the plasma focus. And last year we elaborated their work, and we actually got pretty good agreement between theory and experiment. The theory shows that
Excuse me, this viscosity, you must have a gradient
what?
in the velocity field, right?
That's right.
And you have a strong gradient.
Right.
Is the concept of viscosity in this regime valid or not?
Yes, it definitely is. I mean, as I say, unfortunately, we haven't published the paper yet, so I can't point to it. We presented the paper at APS in October. And yes, the numbers do work out. As I'll talk about in a second, the actual numbers depend on Z effective being different than 1, and we know that we do not have a pure deuterium plasma. But I'll get into that in a second.
Stand a little that way to get on camera. Just that way. Oh, you're on camera.
All right. All right. Well, anyway, the theory we developed shows that the temperature will increase as the B field to the 0.4. So this is one of the reasons, this is one of the benefits we have of having a smaller device which starts with a higher B field and after compression through the process we described ends up with a higher B field. At higher currents than we're currently encountering, we've also predicted that we're going to get electron beam heating through lower hybrid waves, which is basically a resonant wave heating. Now, in terms of efficiency, we can get a measure of the efficiency because we measure the ion beam that comes out with a Rogowski coil. Now, we don't measure every beam because at the moment there's not enough symmetry so that every time the beam goes down our drift tube so we can measure it. But when it does, we get a signal that looks like this. You've got a very clean signal of an early beam well before the neutron production time of maybe 100 or 200 kiloamps and MeV energies, and then you get a littler beam just about the time the plasmoid is reaching maximum density. Now, that early beam obviously is somewhat of a waste of energy, and it's a symptom of what's still going wrong. For a long time, we have known that we're getting less density, considerably less density than our theory predicts. So it's very clear that one of the reasons is this early beam, which dissipates the energy before we get to maximum compression. And you can see the early beam in this graph of di dt, the rate of change of the current. There's a sudden fall, and then there's the big fall with the pinch and the production of the plasmoid. Well, to make a long story short, what we found out from both our work and from other people's research is that the reason for the early beam is that there's actually 2 compressions. The sheath actually has broken apart into 2 parts. The first part The first part compresses, but it's closely surrounded by the second sheath. So we don't get the kinking and we don't get the high degree of compression that leads to neutron production. We get a jet or blob of plasma that moves out of the way, but is still attached to part of the current sheath. And then we get the real plasmoid formation in the outer current sheath, which is no longer affected by this blob. So basically what's happening is about half of our current is not going into the plasmoid.
And the two dark, the twin tower rectangles there, those are the rods.
Right, this is the cathode rods, thanks Derek. This is the plasmoid, and this is what we call the jet or the blob that comes out of the earlier compression.
What is this? Is this H-alpha light? Is this visible light?
Oh, I'm sorry. This is visible. So this, by the way, this is a black and white photo. The color is added just for clarity and aesthetics. This is an ICCD camera with a fifth of a nanosecond exposure time.
So where do you think the peak temperature?
The peak temperature is almost certainly inside the plasmoid. Obviously, what we're seeing is the glowing semi-ionized that's on the outside. So the plasmoid is obviously smaller than what we're measuring. We don't know exactly, so we can put lower limits on the density.
If you have a current density, what is the role of reconnection? You know, every current density layer, current sheets are subject to reconnection.
Well, basically within the sheath that forms the plasmoid, this is magnetized. So that's going to discourage reconnection. But clearly in the outer sheath has formed through reconnection and is not adequately magnetized. I'll get into that in just a second. What we think forms the double sheath is the disruption of the filaments. Let me just get a little out of order here. This is what we should be seeing approaching. If we're looking straight down the machine, we should see the filaments as we approach the pinch. This is 40-year-old work from Dr. Bostic, who was the one who introduced me to this machine. But we don't see that. We do not see the filaments as the pinch approaches. So at some point, the filaments have been disrupted. What we know is that the filaments do exist during the period in which the sheath is moving outward from the teeth where they originate out to these rods and then to move upward along to the end of the anode. Because we can see the little trails that they make on the tungsten plate and what's deposited on the tungsten plate, which I'll get to in a second. And we see these little trails, these are about 100 or 200 microns across, coming off the teeth, merrily going their way, and then as they approach the copper rod, they're disrupted. And what they're disrupted by, we're quite sure, is that we have lots of evidence that there's a small amount of arcing where these copper rods screw into the plate, and that's producing a big increase in impurities, which disrupts these filaments. Now, we think we can get rid of that arcing, and that's what we're working on right now, by basically better connection, by using indium or indium solder. If we can't do that, and if we can't maintain that at higher currents, then what we're going to do is move to a single cathode, which is going to be created out of tungsten copper, so that we aren't going to have a join at all. And also, I don't know whether you can probably not see it at this scale, but there's going to be a taper, an on-ramp, as it were, to get the filament smoothly around this 90-degree bend. Now, we're very confident that if we can get the filaments, which are already concentrating the field, and magnetizing the plasma all the way down to the end of the anode, we're going to get a big jump in density, basically about a factor of 50 to 100. So that's what we're looking to do right now. Now, filamentation is absolutely fundamental for our process, but it's fundamental for most of your processes too, except you don't want the filaments. Because in your case, if you're trying to get a stable plasma, the filaments will allow the plasma to work its way through the confining magnetic field and dissipate. I think filamentation, a joint collaboration that studies the filamentation process that's ubiquitous in plasmas both in the lab and in the astrophysical context, whether they're desired or undesired, would be a terrific way of our all collaborating together. Because we all need improvements in theory, in simulation, and, as one of our colleagues mentioned this morning, in diagnostics. Because a lot of these filaments are actually quite hard to observe. What is their temperature? What is their density? But some of you have already solved these problems. So I think this is a terrific area for collaboration among all of us, and it's very concrete. So where do we go, just like what's next over the next year or so? If we preserve the filaments, we should get up to our theoretical density for 1.2 megaamps, which is about 8 times 10 to the 21st per cc. If we increase the current to 2.8 megaamps, which we can do by putting on all 12 capacitors, going up to our full 45 kilovolts, shortening the electrodes, and doing other things to reduce inductance, then we get up to about 4 times 10 to the 22nd. Now, the compression itself becomes more efficient with heavier gases. So when we finally go to PB11, we think there's going to be a big jump, about a factor of 25, to get up to our aim, which is very high density, 10 to the 24th per cc. Now, even at these densities, we only need metastability. For net energy production, we only need about 1,500 ion orbits. So that's not much. We don't need millions or tens of millions, which is the stable condition most of you are aiming for. That's because we have very high energy density and very high particle density. Now, how are we going to deal with Bremsstrahlung? Because Bremsstrahlung is going to be cooling this. The effect that comes to our aid is this quantum magnetic field effect. I hope I have time to describe it very briefly. Basically what happens is any electron, hello? Any electron is orbiting around its magnetic field line. If it's a strong enough field, then you have to take into account that its angular momentum is quantized, and it can only orbit at certain quantum levels called Landau levels. If a passing ion does not have enough momentum to kick it into the next Landau level, the ion cannot transfer energy to the electron. So what happens is, at high magnetic fields, there's a drastic reduction in the efficiency of energy transfer from ions to electrons, which does not affect the energy transfer from the electrons to the ions. What? I'm getting to that. Just a second. So at the level that we are aiming for, would be more than 3 gigagauss, QMEF will reduce the electron temperature by more than a factor of 20 and cut X-rays by 4 times, which will allow the ignition, by my definition, of PB11. We have a ways to go before we get there. I'm going to skip this. We can do it during discussion. This is just the arithmetic that gets us to this is 11 eV per gigagauss of electron energy, and the ion energy is going to be higher by the ratio of the masses. I'm just going to skip over that one for time. Basically, the level of the magnetic field we're getting now is of the order of 0.06 gigagauss. What we theoretically expect right now is 10 times higher. With the filaments, we expect 0.6 gigagauss. With full current, about 1.3 gigagauss. With the greater compression with PB11, 10 gigagauss. Somewhere between here and here, we should be able to see that quantum effect start to come in very clearly. And we'll see it because the electrons will be much cooler. So just to summarize, these would be the steps we see getting to a demonstration of feasibility. With DD, we're presently getting a yield of 0.2 joules per shot. With the filaments intact, we should get about 2 joules per shot. With full current, about 60 joules per shot. When we mix in heavier gases, about 1,500 joules with deuterium, although we'll probably dilute it just for safety purposes. With PB11, about 30 kilojoules to demonstrate feasibility. I guess you're signaling, am I out of time?
You got a couple minutes.
Okay, we'll just take care of the rest in questions. So thanks for your attention.
All right, we have a couple minutes for questions. Questions? Anything?
I think you're saying, if I did the arithmetic right, that you've got about 6,000 Tesla in your current experiments.
Right.
And so this should have some pretty dramatic effects on the spectroscopy of anything in there. Be kind of fun to see it. Have you diagnosed, looked at lines and all kinds of effects from this?
As I say, we've been pretty limited by our staff. We're just right now setting up a UV spectroscope. So we don't have any spectroscopic. I'm sorry. We're just setting up a UV spectroscope, so at the moment we don't have any spectroscopic data. I'd be happy to discuss what we should expect because, as I say, we're just at an early stage of setting up that diagnostic. We do have the equipment, but it's not working right now.
You guys have been talking enough. I'm going to go right here.
That's all right. I can ask later.
Yes, you get a whole science fair.
Since you rely on instabilities or a series of instabilities to assemble this thing in a desired way, since you're relying on instabilities so heavily, what does this do to the repeatability of?
Good question. Obviously, repeatability has always been a problem with the dense plasma focus. You do get a lot of difference shot to shot. Now, with our machine, we've got it to the point where it's clearly a non-Gaussian distribution. We can get 5 shots in a row that you can lay right on top of each other. And in fact, sometimes I wondered whether Derek saved the wrong data. But the 6th shot could be off in yield by as much as a factor of 2. So if you take everything, you're going to have a factor of 2 variation in almost any of these variables. But it's not Gaussian. It's obvious that you've got a semi-stable mode of operation. Second of all, I think it has a lot right now to do with the impurities. Because as long as we're forcing impurities, copper, silver, whatnot, then you're going to get a lot of variabilities. These instabilities, of course, will be very sensitive to the effect of Z.
One more? Quick one. Famous last words.
So since you said the impurity, you talk about Bremsstrahlung and so on, but the line radiation would be pretty big. The line radiation loss must really influence the confinement of your system.
Well, once the plasmoid heats up to these very hot temperatures, certainly with deuterium, you've got no line radiation. As I say, what we're looking at in the visible is obviously the outer core, the outer, I'm sorry, whatever the opposite of the core is. The outer shell of the plasmoid is what we actually see. The plasmoid itself must be smaller and is completely ionized. Even with boron, boron's completely ionized by the time you get to, you know, 1 keV. So the line radiation can be interesting and important on the way down, but by the time you get to the plasmoid, everything's totally ionized. It's basically brimstone.
Well, we gotta start. Science camp. Okay, we'll hear one last question, Tom, just because you're nice and more time.
So Eric, you've proposed the PB11 essentially outcome. What's stopping you from using a DT reaction just to show that you can scale the physics up beyond what's been done with previous plasma-focused devices?
Okay. Well, first of all, we haven't. In other words, to get more than 2 joules, to get more than 1 joule, which has been the level that previous plasma focus has achieved with pure deuterium, you obviously have to compare apples to apples. It won't be impressive if we get it with DT. People have already gone beyond 1 joule with DT. Second of all, it really doesn't gain us much because it will make everything radioactive. So right now, with the DD neutrons, which, you know, are only 2.45 MeV, we can't detect any radioactivity. It's absolutely at background. So we just don't want to, there's no reason to deal with DT. If we go up, it's going to be impressive enough that we're doing it with pure deuterium. And as I say, to go where we want to go, we have to go to PB11 because that's the whole point. So I don't think that we have an intermediate stop. We'll go directly from DD to PB11. The only intermediate stop is we are going to mix the PB11 in, you know, like the horses, the hay and the oats, because I think that's going to be easier to deal with gradually with some of the effects of the boron, like the boron plating out all over the place and other fun things like that.
You do intend to show DT break-even operation for you?
With DD. With DD. There's just no reason to use DT itself. I don't think it's, we want to show a very high level of operation with D. Will it be break even? Yeah, I guess it would be. It would be break even with DT by extrapolation, but we're not going to use DT. We're going to use DD. No, we couldn't get DD.
Just if we extrapolated to the DT from where we are with the DD, then that hypothetical DT would be break even.
Right.
But we won't
But
actually
we're not going to either get real break even with DD or real break even with DT, which will make our facility radioactive.
Moral equivalent.
Right. Thanks.
So Mike, you guys try alphas next.